My name is Madina Latifa, and today I will be introducing a demo on how to automatically generate the synchronization infrastructure between multiple notations for blended modeling. We will first begin by introducing our meta models. In this example, we will be using UMLRT for state machines formalized with two abstract syntaxes or meta models. On the left, we see the meta model used in Papyrus RT, for which we instantiate graphical models, while on the right, we see the meta model generated from the textual grammar of HCL, for which we instantiate textual models. Step 1. Define mapping models. First thing that we need to do is to create mapping models so that we can define links between elements of these two meta models. So we continue to do so. We first define the mapping model, and here we give the mapping model a name. The root will be model. So here we have our first mapping model, and we see that we have also the textual editor. First thing that we will do is that we will start by defining the mapping model name, and then we will continue with the source meta models, which in this case will be state machine is the name of the package of the source meta model, and the target meta models here with this HCL scope. Now that we defined the mapping model, source meta model, and target meta model, we need to define the mapping rules. In order to give you a better overview of the mapping rules throughout the rest of the demo, we will be showing the tree-based editor. So here we defined a new mapping rule. In this mapping rule, we want to map a state machine element to a state machine element. So we select the source and the target elements. So in this case, we only needed to define the source and the target. The user can, of course, add a comment, which is optional. There is no need for condition, helper literals. The name will be automatically generated, and the operator had no value in this case, in this particular case, because we are mapping two e-classes, and it will not generate anything in the model transformations. Next, we define a child mapping rule, which will be mapping e-references. It will map the top e-reference of the state machine in the source meta model with the state e-reference of the state machine in the target meta model. We fast forward the definition of the graphical to textual and textual to graphical mapping models, as we will present more details after the generation of the model transformations. Step 2. Run higher order transformations. Now, after the definition of the mapping models, we need to run the higher order transformations that will take the mapping models as input and generate the QBTO model transformations. So we run them, and we need to specify the path of the mapping model. We start with the graphical or textual one, and then we also need to specify the path where the model transformations will be generated. We run them, and then we check here, we do a refresh, and we see that we have generated the graphical to textual model transformations. And we will do the same also for the textual to graphical mapping model. We specify the path of the mapping model, and we also specify the path of the generated model transformations. Once again, we do a refresh, and we see here that we have generated the textual to graphical mapping, the textual to graphical model transformations. Now we will make a comparison between the textual to graphical mapping model and the generated textual to graphical model transformations. So here we once again open the textual to graphical mapping model. And now we want to see them side by side. Now we will begin with the state machine to state machine mapping rule. As we can see, we have defined two mapping rules mapping the same concepts. However, for the first one, we have defined a condition. If the condition evaluates to true, the first state machine to state machine mapping rule will be executed. Alternatively, the second one will. So we can see that the first and the second state machine to state machine mapping rules are generated as state machine to state machine 0 and state machine to state machine 1. Now, what is interesting in this case is that we have another state machine to state machine mapping rule, which is disjunctive, named state machine to state machine disjunct. Being that there exist two rules with the same name, the higher order transformations have generated a disjunctive rule so that the first mapping rule whose condition evaluates to true will be executed. The user does not have to define anything related to this disjunctive rule or the list of the disjunctive rules, only has to define these two state machine to state machine mapping rules. This logic can of course also be achieved with an if-else statement, which we do support with the help of helper statements. But we wanted to show a more simplistic way of doing it, which can also be more intuitive for domain experts. And this is not the only case of disjunctive rules. So here we also have transition to transition disjunct. In the mapping model, we have no information that in the model transformations there needs to be a disjunctive rule. So we have only defined transition to transition, and we have defined other rules related to transitions. And automatically, by analyzing the input from the mapping models and the involved DSMLs, the higher order transformations are able to generate the disjunctive rules. Moreover, we also support the concepts of abstract mappings and inheritance. For example, the user does not have to specify that this mapping rule is abstract or that the mapping rule inherits another, because the higher order transformations do that automatically based on the input information. The user doesn't have to invoke the rules either, because once again that is done automatically by iterating through the mapping rules that are defined in the mapping model and checking which one has the appropriate source and target. So this means that the user is not only relieved from writing the model transformations, but also the amount of information that is required from the user side is minimized. Now, as we could see, we had to define the source and target elements to map between two concepts in this example. But there are also cases when a concept in the target meta model does not have a source, does not have a match in the source meta model. An example that we have here is the composite state. So here we see that we have defined a null to top mapping rule, which has no source, but has a target. A target in this case is composite state. And the way that this is interpreted by the higher order transformations is that in the model transformations, we need to create a composite state object. So these are a few of the things that are supported by our solution. Now let us proceed further. Step 3, run model transformations. What we will now do is we will run the generated model transformations. Here we have a graphical model, and we will run the graphical to textual model transformations to generate the textual model. So we run the graphical to textual, and we see that we want to generate a textual model. And here now we have generated the textual model. Now let's see how the changes can be propagated from one to the other. Let's start with a simple one. Let's say that we just want to change the name. So the moment that then we run the textual to graphical model transformations, then we can see that the name of the state is changed. Then we can also try to delete a particular, let's say, transition. In this case, let's delete T1, which is here. Let's see what happens. So we delete this, we save it, and we run the graphical to textual model transformations once again. And here we see that do not have transition T1 anymore. We have now reached the end of this demo where we showed how to define mapping models starting from two meta models, how to use these mapping models as input to higher order transformations to generate model-to-model transformations in QVTO, and how to use this model-to-model transformations to propagate changes between a graphical and textual model. Thank you for watching.